Hi, this is Tzvi Rosen. Today we're going to be talking about applications of integration to the computation of surface area. First, we'll derive the formulas. Let's start with the surface area of a cylinder. And here you can think about a can of beans. What is the lateral surface area of a cylinder? In other words, the area around the sides, not including the top and bottom circles. Well, if we take that can of beans and envision the sides as a label, you snip off the label and you measure the resulting area. And that will be 2 pi RH. What about the surface area of a cone? Okay, and here the cone has, as a base, a circle of radius r with length along the side L, given by L. If you slice the cone from the base to the vertex and then you flatten it, you'll get a sector of a circle. Okay? And the radius of that circle will be L, which means that the corresponding circle has area pi L squared. But we're not taking the whole circle, it's only a sector, so we have to determine what percentage of that circle is there. Well, we can determine that by looking at how much of the total circumference this partial circumference is. So the partial circumference is 2 pi r, since it comes from this circle of circumference 2 pi r at the bottom of the cone, and the total circumference is 2 pi l, so the portion of the circle is r over l. Therefore, the area of the sector is that portion times the area, so r over l times pi l squared, which gives us pi rl. Now we'll compute the surface area of a frustum. And a frustum is a portion of a circular cone between two circles, as pictured. Okay, and this might not be a shape that you've seen before, but we'll be using it extensively in this lecture, so we should get familiar with it. So here we have the bottom circle is radius r1, the top circle is radius r2, the length of the portion that we have of the cone is L, and the length of the missing part of the cone is L1. So then the area is the area of the large cone minus the area of the removed cone, which is, from what we just computed, pi r1 times L plus L1 minus pi r2 times L1. Using similar triangles, we note that r2 over L1 is equal to r1 over L plus L1 because we have these corresponding triangles. These are similar, the smaller one and the larger one. This is 2r1 and this is 2r2. This is L, and L1 means that the large length is L plus L1 and the small length is just L1. So that's what gives us this equation. And it implies that R1 L1 is equal to R2 times L plus L1. So the area, substituting into the expression we computed above, is pi times, or first we just expand the multiplication. We get pi times R1L plus R1L1 minus R2L1. Because we have R1L1 over here, we can substitute it in for this term to get this term. We get pi times R1L1 plus R2 times L plus L1 minus R2L1. And further simplifying, we eventually get pi L times R1 plus R2. Okay, so that's the surface area of a frustum. Now let's think about a surface of revolution. Consider a curve defined by y equals f of x, which is then rotated around the x-axis. And here is a couple of images that I made in Blender. The first is a curve, and the second is a surface of revolution. We need to approximate the surface by smaller pieces whose surface area we know how to compute, like we did with volume. So this is a familiar strategy. You approximate with small pieces, and then you take the limit as those pieces become infinitesimal. And you'll eventually get an integral. But what pieces should we take? Cylinders don't work. If we tried to cut it up into cylinders and then just take the approximation of the area given by those cylinders, it would be like trying to approximate the length of this line using this jagged line. You end up missing things that are happening on the diagonal because you're just getting basically the same thing as if you had just gone down and across. Even though the jagged line looks much closer to the diagonal line, it still ends up having the exact same length as going down and then across. And a similar phenomenon happens with these cylinders. You're going down and across as you go along that surface. So we need to find a different tool, and that's where the frustums come in. Maybe frusta. We're going to approximate with these frustums, and you can see just visually that this collection of blue frustums, or frusta, looks much closer to the surface. We're capturing a lot of the things that are happening on the diagonal, even if it's not quite as correctly curved. Okay, and if maybe I'll just bring up Blender so we can see this collection of frustums. Okay, you can see that this does a good job of kind of smoothly approximating the surface that we're interested in. Okay. So we're going to compute the sum of the frusta and then take the limit to obtain an integral. So let's start by getting the sum and turn it into an integral. Above, we computed the area of a frustum as pi L times R1 plus R2. We can take R to be the average of R1 and R2, so that the area of a frustum is 2 pi LR. And we don't have to worry about two different radii. The surface area will be, of the entire surface, S, will be equal to the sum over all x values of the area of the frustum that's situated at position x, which can be written as 2 pi L of x, R of x. And we just factor the 2 pi out of the sum, where L of x is equal to the square root of the change in x squared plus the change in f of x squared. That's the arc length at x, and that corresponds to the L, the length along the side, the length along the diagonal of the frustum. And R of x is given by 1/2 f of x plus f of x plus delta x. Okay, so that's just the average of the value of f at the two endpoints of that interval. Taking the limit as delta x goes to 0 gives 2 pi times the integral from x min to x max of f of x, because R of x, as the x plus delta x and x come together, the value of f approaches just the value of f at x. And then the expression for L of x, which was delta x squared plus delta f of x squared, approaches square root of dx squared plus dy squared, which, as we did in the arc length section, we're going to write in this way. It's the square root of 1 plus f prime of x squared dx. Okay, so we have an integral which will give us the surface area. And to summarize what we do when we're rotating around the x-axis, when y equals f of x as above is rotated about the x-axis, we have s equals 2 pi times the integral from x min to x max of f of x times the square root of 1 plus f prime of x squared dx. When instead of having y as a function of x, we have x as a function of y, when x equals g of y is rotated about the x-axis, we similarly derive s equals 2 pi times the integral from y min to y max of y times the square root of 1 plus g prime y squared dy. A formula that summarizes both is s equals the integral of 2 pi y ds. And y indicates either y or f of x, and ds is the arc length integral the arc length infinitesimal, and it's given by the two expressions above. Okay. And you can derive similar formulas for rotation around the y-axis. When y equals f of x is rotated about the y-axis, we have s equals 2 pi times the integral from x min to x max of x times the square root of 1 plus f prime of x squared dx. When x equals g of y is rotated about the y-axis, we have s equals 2 pi times the integral of y min to y max of g of y times the square root of 1 plus g prime of y squared dy. A formula that summarizes both is integral of 2 pi x ds. And again, here we have, this could either be x or g of y, and this could be either expression in terms of the arc length infinitesimal. Okay. Now let's do some examples. Example 1. Determine the area of the surface obtained by rotating the curve y equals x cubed for 0 less than or equal to x less than or equal to 2 about the x-axis. So let's start by envisioning what this looks like. So if we have a curve y equals x cubed from 0 to 2, so at x equals 0, y is equal to 0 cubed, or 0. And then we have 1, 2, and then the point of y equals x cubed corresponding to x equals 2 is y equals 8. Put this high up there without drawing the tick marks because it'll be inaccurate. And we get something that looks like this. Okay. So rotating this about the y-axis about the x-axis, will give us something that looks like this kind of horn thing. Okay. So yeah, that's our surface of revolution. So now that we have a sense for what that might look like, we're going to use the formulas that we derived to compute the surface area. So we note that we're using the x-axis, which means that the correct formula is integral of 2 pi y ds, and we note that that y is a function of x, so we should translate everything into that form, which gives us x min to x max of 2 pi f of x times square root of 1 plus f prime of x squared dx. Okay. We'll note that f of x, f of x equals x cubed, and f prime of x equals 3x squared, which means that our surface area will be given by the integral from x min, which is 0, to 2, and I'll write that here for completeness. X min equals 0, x max equals 2. Integral from 0 to 2 of 2 pi x cubed times the square root of 1 plus 9x to the 4th dx. Okay, now we can factor out our 2 pi and start thinking about how to integrate this expression. So whenever you have some function inside of another function, as well as some extra stuff outside, a good thing to start thinking about is a u substitution. So it turns out here that just to input this whole thing as u will give us u equals 1 plus 9x to the fourth, and du equals 36x cubed. And this is precisely, this will be, it will be able to use the x cubed here, dx, it's important. We'll be able to use the x cubed dx that we have and just multiply by a constant to complete the u substitution. Okay, so let's grab this integral along with the u substitution. Apologies. Okay. Let's return to the drawing tool. Okay. Plugging in our u substitution, we have 2 pi times the integral from, we have to change our bounds. Plugging in x equals 0 gets us plugging in x equals 0 gets us u equals 1, and plugging in x equals 2 gets us u equals 145. Okay. And the rest of the substitutions, so we're plugging in u inside of the square root, and then x cubed dx becomes du over 36. Okay, and that's equal to pi over 18, just factoring out the 1 over 36, integral from 1 to 145 of u to the 1/2 du, which is equal to pi over 18 times 2u to the 3/2 over 3 from 1 to 145, which is given by pi over 18 times, and let's bring the 2/3 out actually. So we have pi over 27 times 145 times the square root of 145 minus 1. And that's our answer. Okay, so that's the surface area of this surface of revolution. Let's do another example. This time we'll be rotating around the y-axis. Determine the area of the surface obtained by rotating the curve y equals quarter x squared minus 1/2 ln x for 1 less than or equal to x less than or equal to 2 about the y-axis. So again, let's get a picture of what this looks like. So we have x from 1 to 2, and we have y equals a quarter x squared minus 1/2 ln x. At x equals 1, ln is 0, and x squared is 1, so we have y equals a quarter. And at x equals 2, we're going to have 1 minus half ln 2. So ln of 2 is a bit less than 1. So we'll have something like a quarter to a half-ish. So let's say it looks something like this. A quarter over here, and 1 minus ln 2 over 2 here. Okay, and we're of course going to rotate this about this time about the y-axis, which means it'll look something like this. Okay, you get this nice tunnel-looking thing. Okay, so now we should write up the formula for the integral. And we do that first by observing which axis we're rotating around. Because we're rotating around the y-axis, we're going to use integral of 2 pi x ds. Okay, it's always the other variable. So because we're rotating around the y-axis, it's 2 pi x, and the reason being that the radius is given by the x coordinate. And then we're going to note that it's, again, y equals f of x. So our formula becomes the integral of 2 pi x times the square root of 1 plus f prime of x squared dx, going from x min to x max. And now we'll fill in the details. F prime of x is given by, so we apply the power rule to the first term to get x over 2, or a half x, minus ln x has derivative 1 over x, so we have 1 over 2x. We don't actually need f of x itself for this integral, so we just need x min, which is 1, and x max, which is 2. Okay, so our integral becomes s equals integral from 1 to 2 of 2 pi x times the square root of 1 plus 1 half x minus 1 over x, just factoring that derivative, and we're squaring this, dx. Okay. If you think back to the arc length section, you might have an intuition for what will happen to this integral. So if we simplify this expression inside the square root, what we obtain is 1 plus 1/4 x squared minus 2x plus 1 over x squared. And when you, I'm sorry, that should not be 2x. X squared minus 2 plus 1 over x squared. And when you add in the 1, what you obtain is, so minus 2 over 4 is minus a half, plus 1 is plus a half. So this becomes 1/4 x squared plus 2 plus 1 over x squared, which, as you might remember, is equal to 1/4 of x plus 1 over x squared. Okay. So plugging that back in, we have integral from 1 to 2 pi x times the square root of 1/4 times x plus 1 over x squared dx. Okay, so the square root of a square obviously is just the thing itself. So let's factor out the 2 pi as well. We have 2 pi times integral from 1 to 2 of x times 1/2 x plus 1 over x dx. Okay, we can pull out a factor of a half, and we get pi times integral from 1 to 2 of x times x plus 1 over x is x squared plus 1 dx, which gives us pi times x cubed over 3 plus x, evaluated from 1 to 2, which is at the first point, it's 8/3 plus 2, or 14/3. And the second point, it's 1/3 plus 1, or 4/3. So we get 14/3 minus 1/3, minus, 4/3. And we have, in summary, 10 pi over 3 as the area of our surface of revolution. We'll pick up now with example 3. Find the surface area of a sphere of radius r. Okay, so this is a bit of a different type of problem because we have to first we have to introduce the equation for the curve, and then we can go ahead and translate it into a surface area integral. So let's start by drawing a circle of radius r. So we have r minus r, r minus r. So this is our circle, poorly drawn as it may be. But we'll notice that there'll be a lot of redundancy. So whichever axis we rotate around, it's going to pass through its reflection. So what we'll do instead is we're going to limit it to just this arc of the circle here. And you'll notice that when we rotate that around the x-axis, we'll get a hemisphere. So we'll note that we're just computing the surface area of a hemisphere. Okay, well, what's the equation for this arc of the circle? We can compute x as a function of y. We can compute y as a function of x. So how about this? How about we rotate around the y-axis and we compute y as a function of x? Okay, so we have y equal, well, we'll start with the equation for the circle. We have x squared plus y squared equals r squared. And what this gives us in terms of, when we try to solve for one of the variables, we have y equals the square root of r minus x squared, where x goes from 0 to r. Okay. So now we'll set up the integral. We have that the surface area will be equal to integral of 2 pi, and now we have to decide which way we're rotating. Should we use the x-axis or the y-axis? Let's use the x-axis. Okay, so we'll take it around the x-axis. 2 pi y times ds, and we're going to use 2 pi y times the square root of 1 plus f prime of x squared dx. So plugging in f, we have to compute f prime of x. Oh, and we'll also need x min and x max. So f prime of x gives us 1 over 2 root x, applying the power rule, 2 root r minus x squared times minus 2x, that's the chain rule. So we end up with minus x over square root of r minus x, r squared, I'm sorry. This should also be r squared. R squared minus x squared. So plugging this into our formula, and also y we know from above is equal to the square root of r squared minus x squared. So we have, and I'm just going to start this on the next page. We have the integral, and let's also note what x min and x max are. X min is 0, and x max is r. So we can take the integral from 0 to r of 2 pi And now our expression for y is the square root of r squared minus x squared times the square root of 1 plus, now we have to square the derivative, which was minus x over root r squared minus x squared. And that's squared dx. This is the surface area of the hemisphere. We'll take out the 2 pi, 0 to r, root r squared minus x squared times the square root of 1 plus x squared over r squared minus x squared dx. So we want to put this over the same denominator, so we have r squared minus x squared over r squared minus x squared plus x squared divided by r squared minus x squared. And we get some cancellation, and we're left with r squared over r squared minus x squared. And when we put that inside of the square root, we're left with root r squared minus x squared times the square root of r squared on top is r over square root of r squared minus x squared on bottom dx. Well, now we get cancellation of these two. So we can just compute 2 pi times integral of from 0 to r, and the r is itself a constant, so we can pull that out, dx, and this equals 2 pi r times x from 0 to r, which is 2 pi r squared. Okay, so to answer the question above, the hemisphere has a surface area of 2 pi r squared, which means for a sphere, the surface area would be twice that, or 4 pi r squared. And that is, in fact, the formula. You get 4 great circles, gives you the surface area of a sphere. Okay, so we'll finish it off with just a summary of the strategy for how you approach these problems. The first step is to identify whether y equals f of x or x equals g of y is preferred. And you can use either of those in most problems. Then you identify the axis of rotation and use the appropriate formula. If you're rotating around the x-axis, use integral of 2 pi y ds. And if you're rotating around the y-axis, use 2 pi x ds. Okay. Next, you compute your f prime of x squared or g prime of y squared to stick it into the ds, and you simplify the integral and integrate what remains. Okay, best of luck.